You ever stop and think about how the internet actually works? I mean, how can a single live stream hit your screen at the exact same time as millions of other people? And how does a private chat know to only go to your one friend? It all feels like magic, right? Well, it's not. It's actually a set of super clever rules. So let's break down how the internet really talks, from a private whisper all the way to a global shout. No, really, just think about that for a second. You've got one server somewhere out there pushing a massive, high-definition video feed to millions of us all at the exact same moment. How does that not just completely break the internet? That fundamental puzzle is exactly what we're going to solve right now. All right, so to understand how we get to millions, we have to start with one. The simplest, most fundamental way computers talk to each other is something called Unicast. And trust me, this is the foundation for everything else we're going to talk about. Unicast is pretty much exactly what it sounds like. One source sending one message to one single specific destination. You use it all the time. Every time you click a link to a website or send a direct message, yep, that's Unicast. It's just a simple point-to-point conversation. You know, the best way to picture this is with old-school mail. You write a letter, you put one specific address on the envelope, and it goes to one and only one house. The mail carrier isn't dropping a copy in every single mailbox on the street. It's a direct, private, one-to-one delivery. Simple as that. And this diagram? It shows the digital letter's journey perfectly. See? A packet of data leaves the source, and every single router it hits along the way just looks at that final address and sends it down one specific path. There's no guesswork, no duplication. It's a direct, private line straight to the recipient. Okay, so one-to-one makes perfect sense, but what if you need to do the exact opposite? What if you need to shout a message so that every single device on a network hears it instantly? Well, this is where things start to get really messy really fast. This method is called broadcast, and it is the polar opposite of Unicast. This isn't a private letter, it's a giant, blaring public announcement system. One source sends out a packet, and the network's job is to make sure it gets delivered to all the other nodes. But how on earth do you do that without creating total chaos? Okay, so the most obvious way to do this, the naive approach, is, well, just flood the thing, right? The source just sends a copy to its immediate neighbors. Then each of those neighbors turns around and sends copies to their neighbors, and so on and so on. It sounds like it should work. But here's the thing. Real networks are messy. They have loops. And in a network with loops, this super simple idea creates an absolute catastrophe. And that catastrophe? It has a name, and it sounds as bad as it is. The broadcast storm. It's basically a digital hurricane of endlessly duplicating data. You can see exactly how it happens right here. A packet gets sent from A to both B and C. But since B and C are also connected to each other, they start forwarding the packet back and forth and to their other neighbors, and then back again, forever. These packets just multiply exponentially, and pretty soon the entire network grinds to a screeching halt. So yeah, uncontrolled flooding is a terrible, terrible idea. This disaster forced network engineers to come up with some incredibly clever ways to get all the benefits of broadcasting without, the catastrophic storm. It's all about adding a little intelligence to the system. And this quote, it really hits the nail on the head. You can't just turn the fire hose on full blast and hope for the best. The solution isn't to stop flooding altogether, but to flood smart. The network itself needs rules to know the difference between a brand new message and a useless, noisy echo. And here's one of the most brilliant solutions. It's called reverse path forwarding. It's actually a pretty simple rule. When a router gets a broadcast packet, it just asks itself one little question. Hey, did this packet get to me using the shortest possible route from where it started? Let's look at router C here. It gets a packet that started at A, but it came through router B. Now C is smart. It knows the fastest way back to A is that direct connection, not the scenic route through B. So it just goes, nope, this packet from B is a duplicate, and it just drops it. Gone. That one simple rule breaks the loop and kills the storm before it even has a chance to start. Genius, right? But there's an even more elegant fix, and it's called a spanning tree. Instead of just dealing with duplicate packets, what if you could just prevent from ever being sent in the first place? Before any broadcast even happens, all the routers talk to each other, and they agree on one single loop-free path that connects everyone, kind of like the branches of a tree. Now, all broadcasts only travel along this pre-approved path. Everyone gets one copy, and only one. No loops, no storm, no problem. So, We've got one-to-one covered with Unicast, and we have one-to-all with broadcast. But what about that all-important middle ground? What if you want to send a message not to just one person and not to absolutely everyone, but to a very specific self-selected group? This is the exact problem that things like live streaming run into. You definitely don't want to broadcast a 4K video feed to every single device on the entire internet. Can you imagine the waste? You only want to send it to the people who have actively chosen to watch it. And this slide shows the two options perfectly. Over on the right, you've got the brute force way. The source server has to send a separate, identical video stream to every single viewer. This is crazy inefficient and would just crush the server. But look at the left, that's multicast. Here, the source sends out just one stream. The network itself is smart enough to duplicate that stream, but, and this is the magic part, only at the very last second, right where the path splits to reach different groups of viewers. I mean, the bandwidth savings are obviously gigantic. But there's a more fundamental difference here, and it's all about control. With the brute force method, the sender has a list, and it pushes the data out to everyone on it. With multicast, the receivers are in charge. They tell the network, hey, I want to tune into this stream, and they effectively pull the data towards them. Now, this might all sound a little abstract, but I guarantee you are using this technology every single day. Multicast is the invisible engine humming away behind some of the most demanding things we do on the internet. Just think about the tech that basically defines our modern internet. The live streams we keep talking about, the frantic action in an online game where everyone's position has to be perfectly synced, massive video conferences, even the high-speed stock market data feeds. None of it would be possible at scale without the quiet efficiency of multicast working its magic in the background. Okay, final pop quiz to really make sure this all clicks. If multicasting is so great for sending something to a group, why isn't sending a group email considered multicast? I mean, it feels like it should be, right? It all comes back to that idea of control. When you send a group email, your server is basically just sending dozens or hundreds of individual Unicast emails from a list you created. That's a push from the sender. When you watch a live stream, you are the one telling the network, hey, I want to join this multicast group. You're pulling the data to you. It's the difference between being sent a bunch of letters versus tuning into a radio station. So, there you have it. We've gone from a simple one-to-one message to the absolute chaos of the broadcast storm, and finally to the elegant, efficient solution of multicast. It's a perfect example of how the internet is built on these incredibly clever ideas that solve massive problems, which really just leaves you with one big question. What's the next broadcast storm that today's engineers are trying to tame?